All right, everyone, this is section 3.3, properties of logarithms. So in our last chapter, we talked about logarithms, the inverse operation to exponential functions. And what we're going to talk about today is how those properties of exponents that we've dealt with already show themselves in our logarithms. So the first formula we're going to work with is what we call the change of base formula. This change of base formula allows us to evaluate logarithms when the bases are not quite as compatible, right? We saw, log base 2 of 8 is easy to find. That's an integer answer. But sometimes we'll get some logarithms that aren't quite as clear, and we can use our calculator to change the base. So regardless of what we use for our base, whether it is base b, base 10, or base e with a natural log, in all three cases, the formula looks the same. We take the logarithm of the base and put that into the denominator, and the logarithm of the argument, the value that we are taking the logarithm of, in the numerator, and we can just calculate that value. The way that looks most often is with a logarithm like this. We have log base 7 of 15. We can use either the common log base 10, to rewrite this as the log of 15 over the log of 7. And we could plug that directly into our calculator. We'll get 1.392. We could do the same thing with the natural log of 15 over the natural log of 7. Again, we'll get the exact same answer. This should make sense, right? This number is the number we would raise 7 to in order to get 15 as a result. So what we can see here is that it doesn't really matter what base we use when we use the change of base formula. So we want to use whichever one's most convenient. You can see here the change of base formula may be used to graph logs that are not base 10 or base e. And we could do that if we'd like by graphing y equals log base 2 of x. We'll talk more about, the way that would look in our graphing calculator is in our y equals screen. We would take the log of x and we would divide that by the log of 2. Some of our calculators have some functionality that allows us to change the base without the change of base formula, but it's always good to have this kind of in our back pocket if necessary. When we talk about properties of logarithms, more often we talk about these three rules, the product property, the quotient property, and the power property. The way I think about these is that the rules that govern exponents also govern logarithms. So if I say had x to the second times x to the third, I would add their exponents and get x to the fifth. Similarly, with our product rule, if I am multiplying some values, I can evaluate each of them as a sum. The same rule applies if I had x to the fourth over x to the second. We could subtract those exponents to create x squared, which is really what's going on with our quotient property. And then finally, our power property says that when we raise a power to a power, we multiply those exponents, right? So x to the second raised to the sixth is the same as x to the 12th. Let's take a look at some examples here. I think I'll try the first two together and ask you guys to try the third one on your own. So we're going to expand this. Our goal here really is to write this so that each logarithm is basically as simple as possible. We will end up with taking one complicated logarithm and splitting it into more than one. So what I notice here is that I have log base 4 of 7x to the fourth times y squared. Well, one move I can make is kind of breaking up this product. I could write this as the log base 4 of 7 plus the log base 4 of x to the fourth plus the log base 4 of y squared. That would be a good first step. We've rewritten this product as a sum of logarithms. And then two of my logarithms have, let me make this a little bit bigger. A couple of my logarithms have exponents, so our final answer here would be log base 4 of 7 plus 4 log base 4 of x plus 2 log base 4 of y. You can see that once we split up this logarithm, our exponents can move out front and multiply our exponents. Why does that make sense? We multiply exponents when we raise a power to a power, which is basically what we're doing with something like y squared. Let's look at another one. Here we have the natural log of the square root of 3x minus 5 divided by 7. So my first move here is I'm going to rewrite this as the natural log of 3x minus 5 raised to the 1/2 power. I find it much easier to work with if we separate this out and use rational exponents rather than a square root. Because we're dividing here, we will now subtract the natural log of 7. My last step here is I can again move my exponent, so I can rewrite this as 1/2 the natural log of 3x minus 5 minus the natural log of 7. So be careful, we can't do anything with that 3x minus 5. We are not multiplying or dividing. So that argument, that value we see in parentheses here, cannot be split up any further. Just that 3x minus 5 will remain. Once you go ahead and try the next example here, log base 6 of the cubed root of x divided by 36y to the 4th. Here you can see my work on this example. The first thing I did is I split up my pieces here. And there's a couple ways we can deal with the negative. For me, it makes most sense if I think about the values that are in the denominator become negative, right? If I have a negative exponent, that creates a reciprocal. So if I have a quantity in my denominator, if I make it negative, that'll account for that negative exponent. The other thing that some people may have overlooked is I evaluated this logarithm in the middle. Log base 6 of 36 is asking me what power do I need to raise 6 to in order to get 36 as a result. Well, I can evaluate that directly as 2. All right, let's keep moving. We mentioned this as we work through some previous examples, but if we have the logarithm of a sum, like here you see log of u plus v, this cannot be rewritten using the properties. The log of 2 plus 3 is the same as the log of 5, which is approximately 0.699. The log of 2 plus the log of 3 would be 0.301 plus 0.477, and we can see that's pretty clearly not 0.699. That's more like 0.778. You can see here, avoid this common error, logs do not distribute. We cannot split up a sum if we're taking the log of that sum. We can rewrite the log of 6 using our properties. We could write that as the log of 2 times 3. And now because we're multiplying inside that logarithm, we can now use our properties. We can rewrite this as the log of 2 plus the log of 3, which we could evaluate to, once the same thing we just saw just up above, 0.778. We will also go in the opposite direction. We can write the expression as a single logarithm. So here we have the log base 4 of 2 plus the log base 4 of 32. And 4 doesn't easily work with exponents into 2, doesn't easily work with exponents into 64. But if we condense these, we can rewrite it as a log base 4 of 2 times 32, which is 64, which we can evaluate. We know that the log base 4 of 64 is 3 because 4 to the 3rd power is 64. Over here on the right, we have the log base 2 of 12 minus the log base 2 of 3. Again, those aren't logs we can evaluate immediately. But if I rewrite this by condensing the log base 12 over 3, sorry, my log base is 2, I really have the log base 2 of 4. Well, that's an easy one to evaluate. Sorry, that's not 4, that is 2. So I want to let you guys try a few examples on your own. Just one quick note before you go ahead and do that. The coefficients of logs must be 1 before we condense them. All right, we need to deal with the exponents first. This is really a matter of order of operations. So here I have 3 times the log base 5 of 4. I'd rather see you make this move first. Log base 5 of 4 to the third, or log base 5 of 64 before we start to condense. Over here on the right, we would want to move this exponent, this 2, up here. We would write this as the natural log of x plus 2 divided by x, because now that I have that exponent, that coefficient of 1, I can now use my condensing rules. So I have the natural log of x plus 2 quantity squared over x. So I want to let you guys try these next 2 on your own. I would suggest pausing the video, working these out, and then check against my work. All right, let's check in and see how we did on those 2. First, we had to rewrite as a single expression. We had the log base b of x minus 2 log base b of 6 minus 1/2 log base b of y. My first move is to get those coefficients dealt with, right? We don't want to deal with those leading coefficients. We want those to become exponents. So the 4 becomes an exponent, the 2 becomes an exponent, and the 1/2 becomes an exponent. You can see I rewrote that immediately as a square root. Then my terms that have negatives out front, those are negative exponents. They end up in the denominator. My positive terms end up in the numerator. Similarly, on the next problem, I condensed what I could inside the parentheses. I moved that 1/3 to an exponent, and then I could rewrite it as either form here, log base 2 of the quantity x squared plus x to the 1/3, or as a cube root, right, log base 2 of the cubed root of x squared plus x. From here on out, I'd like you guys to try these examples. Do your best to make sense of what's going on. Obviously, I will show you my examples, and you'll have the answer key to work from. But I'd like you to see what you can do on the remaining examples. You have 1, 2, 3, 4, 5 to take a shot at. Good luck. All right, let's see how these went. What you'll notice about a lot of these problems is that they really get to, they're really asking you the same operations, right? You know, either condense or rearrange logarithms in a few different ways. On this first one, they want us to rewrite in terms of log m, n, and p. In other words, they want every log to only involve m, n, or p. So we rewrite this, that 3 on the m becomes a coefficient. The n is a square root, so we can think about that as the exponent as 1/2. And the p is in the denominator, which is why we subtract. You can see there, that's about as simple as it gets. On the next problem, they want us to basically simplify the natural log of 1/40e. And so I use my rules to do so. I split this up into the natural log of 1 minus the natural log of 40 minus the natural log of e. You'll also notice that they give us x and y defined as the natural log of 2 and the natural log of 5, respectively. So what they're really asking us to do is to rewrite that log of 40 in terms of 2 and 5. So I rewrote 40 as the product of 2 cubed times 5, which I could split into some logs. And once I have the natural log of 2 and the natural log of 5 down here towards the bottom, I can substitute x in for the natural log of 2, and I could substitute the natural log of 5 in for y. Next, we have a compounding interest type problem. In this case, we are solving for time, right, our variable in the exponent. So what we end up doing is we set up our exponential function and simplify it as best we can. And once we get to this step here, we are no longer able to do much more. So in order to get that that variable out of the exponent, we take the log of both sides. We can manipulate, using our property rules, and then divide this answer out. When it's all said and done, I got about 4.5 years. On our next problem, if we want to evaluate a log, if we want to rewrite a log in exponential form, we first need to condense these two logs into a single log. So that's what I did in my first step. That allows me to rewrite in exponential form, basically eliminating my logarithms, and then solving from there is pretty direct. On our last problem, we have to perform a similar operation. We condense a log, and because we have a log with the same base on both sides of our equation, we can basically ignore it. What we've really done is we've exponentiated, right? We've raised both sides as an exponent on 7. But what we'll end up with is the product of t plus 3 and t minus 2 equaling 2. That's not solvable any other way than through the quadratic formula. Just note here, we always want to check for extraneous solutions. Remember that we can never take the logarithm of a non-positive number, whether it's 0 or a negative number. So we want to check to make sure that our answers are within our domain. In this particular case, our negative answer, negative 1 minus root 33, would not be allowed. So our answer is down here in pink. Only the positive solution, negative 1, plus root 33 all over 2. And we're done.